Alright, this is the explanation video for the part 2 final. For my first question, I decided to do question 2, which is regarding Maclaurin series, and it's specifically about e to the x variations of this function. The first function is the Maclaurin series of f of x squared to the e times e to the x. So this is pretty simple. All we are doing is just multiplying each increasing function by x squared. So 1 plus x squared over 2 factorial becomes x squared plus x times x squared plus x squared times x squared to the 2 factorial plus x cubed times x squared to the 3 factorial, and so on. So our final series will be x squared plus x cubed plus x to the 4th over 2 plus x to the 5th over 6th plus x to the 6th over 24th, and so on. Now we're supposed to evaluate this function at the 100th derivative at 0. So the 100th derivative just with regarding x would be e to the x times x squared plus 200x plus 9,900. Evaluating that just at 0, we will get 9,900. Moving on to part C of this question. It wants us to find the Maclaurin series for e to the 3x. So what we're doing in this problem is just multiplying each of our e to the x functions times 3x. So we will get 1 plus 3x squared over 2 factorial plus 3x cubed over 3 factorial plus 3x to the 4th over 4 factorial, and so on. And for D, we have the function of 3 e to the x. So this will be multiplying each of our functions by 3. So we will have 3 plus 3x squared over 2 plus x squared over 2 plus x to the 4th over 8, and so on. And for part E, we are doing e to the x plus 3. So this is also can be determined as e to the x times e to the 3. So we are again just multiplying each of these e to the x functions times e to the 3rd. So we get e to the 3rd plus e to the 3rd times x plus e to the 3rd times x squared over 2 plus e to the 3rd times x squared over 6, and so on. Our final problem here is find the Maclaurin series of e to the x just plus 3. And now the only difference we'll see here is that we're adding 3, but as we find the derivative of these functions, that 3 is a constant, will return to 0. So it will only be seen on the first part, where we get 4 instead of 1. So 4 plus x squared to the 2 plus x cubed to the 6th, and so on. The second problem I decided to do was problem number 6. And for the first part, we are considering this polar curve from 0 to pi to the 4th, and what happens as as theta approaches pi to the 4th. So we evaluate cosine 1 over cosine theta minus sine theta to pi to the 4th, and we get 1 over the square root of 2 minus 1 over the square root of 2, which is just 1 over 0, or r equals infinity. Part B, we are finding the area of one of these leaves bounded by the bounded by the area of r equals 3 sine 4 theta. So I wrote down our area integral, which is 1/2 r squared d theta. So we evaluate 3 sine 4 theta to this integral. So we have, first we solve for 0 to find our upper bounds. So I found that theta is equal to n pi to the 4th, so our upper bounds will be pi to the 4th, or pi over 4, sorry. So we have upper bounds, our b is pi over 4, and 0, 1/2, 3 sine 4 theta squared d theta. And evaluating this integral, we eventually will get the answer, which is 9 pi over 16. part C of problem number 6, we find all points of 0, theta, pi over 2 pi, where the curve r equals 2 minus 4 cosine theta has vertical or horizontal tangent lines. So what I first started to do was find our derivative of our x function and our y function put into Cartesian from polar. And there I found that our dx d theta was 8 cosine theta sine theta minus 2 sine theta, and our dy d theta function was 2 cosine theta minus 4 cosine squared theta plus 4 sine theta. Putting that together as a slope function, we get 2 cosine theta minus 4 cosine squared theta plus 4 sine theta squared theta divided by 8 cosine theta sine theta minus 2 sine theta. For the y functions, I solved for theta by just setting both of these x and y functions to 0. So I got that our y theta would be 0.5678, 2.2056, 4.0775, and 5.7153. And our x thetas equal pi, 2 pi, 1.318, and 4.96506. I don't really know how to find the x component of this problem. These are the y components, so I got stumped on finding the specific x components that relate to each of these y components, unfortunately. So for my last problem, I decided to do problem number 8, where we decide whether or not the following limits are indeterminate or not, and explain your thoughts if they're not indeterminate. So our first one is the limit as x approaches infinity of 1 over x to the x power. And evaluating this at infinity, we get 1 over infinity to the infinity, or 1 over infinity is 0 to the infinity, which will just be 0. This is not indeterminate form, since as we can tell that we evaluate this function, and this function reaches 0. And the indeterminate forms that are included here would be 0 divided by 0, infinity divided by infinity, 0 times infinity, infinity minus infinity, 0 to the 0 power, and 1 to the infinity power. None of these do fit the bill for the specific function, so it is not indeterminate form. For the b, we get the limit as x approaches infinity of 1 plus 1 over x all to the x power. And, well, we found that the limit of 1 over x to the x is just 0. So the only function here is 1 to the infinity, which is in fact indeterminate form. This cannot be evaluated as it is. And for part C, we get the